I'm currently working in one of the. I'm currently based at one of the big tech companies, and this work was done prior and has absolutely no affiliation with the tech company I'm currently based at. And here I am just talking with my Oxford hat on. Okay, so without further ado, let's. Today we're going to be talking about synthetic data and what happens when we train with synthetic data. So very often in our life, we are faced with the very tough challenge of learning what cats look like. And although it may seem natural, I'm sure all of us remember the bright young days where we could not quite distinguish cats from other wonderful animals. And we can certainly imagine that the same sort of thing is happening currently with our models. Very often we want to teach them how to separate cats from dogs. And if we go online and start looking for pictures of cats, sometimes they look like the cat we see on the screen. Sometimes they are actual real cats and pictures are taken of them. And very often nowadays, when you Google for cats, you'll discover pictures of synthetic cats. They're not really cats that exist in the world. They look like cats. Is someone speaking, or is this just... Sorry.
No,
Yeah,
okay.
yeah, cool. But very often nowadays, it's actually pictures of cats generated by models. So on this slide, I use, I think it was Stable Diffusion 2 back at the time when I made the slide deck. And I asked it to generate me pictures of friendly cats. And now let's for a second assume that we're trying to explain to a child what a cat looks like. So we generate a few pictures of cats. And on the left, we see a cat which looks very good. It's sitting in some odd cloth bowl, which is a little bit unnatural, but we can certainly imagine that you're holding some sort of cloth on a hand and the cat is sitting on it. And it's kind of floating in the air in a relatively odd pose. So I'd probably say it's quite unrealistic and improbable that we would take a picture like this, but it's probably possible. At the same time, on the right, we see another generated cat. The background looks relatively probable, but when we start looking at its feet, especially the back feet, we notice that it's not really connected to the body. At the same time, the front feet, the left one, is a little bit off as well. And importantly, for some reason, it's wearing some sort of a necklace, and it looks rather cartoonish in comparison to the rest of the image. So clearly, if we were to show those two pictures to a child and say, those are cats, and next time you see a creature walking on the street, if it looks like it, then this is what is called a cat. Quite clearly, a child, when they do see such a creature, they should not have a problem detecting a cat and saying that this is a cat. Although they may have some sort of misunderstanding of what a cat is, right? Because they may assume that cats, they fly over a cloth, or perhaps they may assume that cats have necklaces that grow on top of it, or perhaps they may assume that feet sometimes are disconnected from the cats. So let's try and ask Stable Diffusion 2 to produce us more pictures of cats. We may discover that some of the images of cats for Stable Diffusion 2 are a little bit odd. So the one on the left, we can clearly see that the features of the cats are clearly there. So we see the fur, we see the feet, but clearly it's misunderstanding what a cat is. So on the left, we see a cat with a head detached and a hand detached from the body, and also some problems with the eye features and the nose features. And on the right, we see problems with the feet, and similarly with the mouth. And on the picture on the right, we see a cat with a single eye and also no mouth for some reason. And it's relatively common to see cats without eyes because of injuries. it's relatively uncommon to see cats without mouth. So now let's ask this question again. If we had a child and we showed to our child pictures of cats, the ones we see on the screen, would they understand what a cat is? And when they see a cat on the street, will they be able to tell that it's actually a cat in front of them? And the answer here is not as obvious as with the previous slide, where cats were actually quite clear, so the signal to noise ratio is quite nice. But in this particular case, we see that the features are correct. So perhaps just by observing the features of the fur, a child would be able to say, okay, this kind of looks like fur of a cat, but I'm not sure about the rest of the features. Then it clearly becomes apparent so that this uncertainty and the uncertainty of understanding of the original model can create quite noisy pictures of the synthetic media itself. Similarly, the objects themselves, like for example, a cat on the left, clearly also a synthetic cat, it can actually give us a very good indication of what an object is and what an object kind of looks like, but actually miss quite a lot of details of the original object itself. And you may also notice that the sort of mistakes that the models make are kind of correlated. So for example, in this image, on the left, very similarly to the images in the first slide, we noticed some sort of abnormalities in the back feet. Here, it's the same. On the left side, it's kind of abnormal at the back of the feet. On the right, a little bit the same. Then there seem to be some sort of problems with the mouth as well. And this is problematic because not only do we observe that the sort of errors that the models that give us the synthetic media are making, they make mistakes. And importantly, those mistakes are correlated amongst each other. And if we were to show continuously such pictures to other models or perhaps children, they may start misunderstanding what reality looks like. At this point, it's important to also bring in an additional distinction in that when we train our models with quote unquote real data, very often this real data, again, quote unquote, is not really good as well. So the picture on the right, for example, shows us a cat, which clearly shows all of the cat features very well. This is what a cat looks like in reality, but it shows it in a rather odd situation, rather improbable situation, where a cat is breaking through a wall or some sort of wallpaper. And this is not the environment in which you usually observe a cat. And this can also introduce additional uncertainty when we are teaching a model. But nevertheless, if we make an assumption that we are capable and we have enough data to decorrelate the noise of our cat features, then we expect our model to be able to tell apart the signal from noise and then ultimately learn quite well what a cat looks like. So an important question to ask here is, can we ultimately learn from synthetic images? Can we explain to a child what a cat looks like from synthetically generated images of cats? The answer is, yeah, we can, sometimes. An important note here is on sometimes, and an important note here on the types of errors we expect a child or some sort of other model to actually learn from the images we present to it. But to summarize here, we can certainly use synthetic images to learn what some concepts look like, or perhaps all of the concepts. We can try and distilling knowledge of one model into another model. But this comes with additional problems, namely the errors of the original model can start propagating into the subsequent models. And those errors, especially if correlated, will be also learned by the subsequent models. And when we talk about ramifications of training with such synthetic data and the additional absorption of those errors by the subsequent models, we refer to this as model collapse. So on the image to the right, for example, you see a picture of a cat. Again, synthetic. It looks like a cat. It's a totally good representation of what a cat is. Again, shown to a child will be able to tell what a cat looks like. But on the bottom, you'll notice there is a tag, a sort of a watermark. And this watermark is produced by the model because the model assumes that the watermark is actually a part of the object because it saw a lot of other objects with the same watermarks on it. And if, for example, the said model was producing the same watermark for all of the images for the subsequent model would similarly learn what this watermark looks like. Okay. So at this point, let's take a quick break and see if anyone's confused with what a cat is supposed to look like, or is everything making sense thus far?
It is. This is great. Yeah.
Yes. What do we mean by model collapse? Yes. So we'll get to defining what model collapse is and what it looks like.
Yep.
But what I wanted to bring with this part of the talk is to say that we can learn with synthetic data, but usually when we produce this synthetic data, the synthetic data comes with its own errors, and subsequent models end up actually absorbing the said errors. Okay, cool. So before going any further, it's important to make a note here that training with synthetic data is actually quite common. We observe this like practically nowadays everywhere. This is an excerpt from the original GPT-4 paper, where I basically wanted to give a few examples of the sort of a system we all use nowadays in production. It's affecting our day-to-day life, where data generated by prior models or other synthetic models is used inside of training regimes, sometimes not necessarily as the sole data source, sometimes as an additional regularizers, but nevertheless, this is ChatGPT is using synthetic data in its training. So it would necessarily observe pictures of the said cats with heads detached from the body and completely wrongly placed feet and with watermarks and so on. So beware. Systems out there are already consuming this potentially broken data. So in the paper, we talk about model collapse, and we define this as a degenerative process which affects generations of generative models, where basically generated data of one model ends up being consumed by a subsequent model that is in turn generating more data and more data. You can think about this as like polluting the ecosystem with more and more data. And what we observe is that in the early stages of model collapse, your model loses some information about reality and mostly about details of the distribution, and more on this a little bit later. And towards the end, we discovered that model collapse forces the models into this very weird state that is as far from reality as it can be. And again, I'll touch upon what it means for language models and vision models and so on in a little bit. So in this setting, we assume that there exists some sort of a real data, and this data is represented as data 0. Then we get some model, we fit the model on top of this original data. Then we use this data to generate some more data. In some of the settings, we assume that the original data is part of the same data. And then important to note here that we sample here uniformly, so it should still be basically the same distribution approximately. And then we build this next model, and the next model is used to produce more data. And then ultimately over time, we produce more and more models. Important note to make here is that although it may seem a little bit unrealistic, very often this is exactly what model development lifecycle actually looks like. You would go online, you would scrape Twitter or whatnot, and you would grab the latest Twitter data because you want to make sure that you generalize to the latest data, and you would fit a model on top of it. And if the previous Twitter data comes from another model, then ultimately this is exactly the sort of a case we would observe. some proportion of this data is potentially going to be synthetic, some proportion is potentially going to be real. It's going to represent some sort of a distribution, ideally the same distribution as was originally, although as we saw with the examples of cats, there is going to be drift inside of the models themselves. So most of our learning nowadays has errors. Here I put simply models probably always have errors, purely because we don't really have any guarantees that the sort of solutions we discover are going to be optimal. Those errors come from three main sources. Well, there are more sources, but usually the most important ones are the three ones. So those are imperfect model architectures. So when we talk about models in theory, we assume they're universal approximators, i.e. they're capable of approximating arbitrary functions to arbitrary precision. And although in the limit theoretically this is true, we do not actually know if in practice this is true as well. So we do not know if a given model is actually capable of approximating the functions that we expect it to approximate. Then we have imperfect learning procedures. We rely quite commonly on SGD or ADAM or other flavors of gradient descent, and all of them are extremely biased in the types of solutions. They are structurally biased in the types of solutions they discover. And importantly, we do not have any guarantees, unless it's a very specific types of functions we're dealing with, of whether they will actually converge to an optimal solution. And if they're not converging to an optimal solution, a true solution, then they are going to be introducing a little bit of error over time. And importantly, we have a lot of statistical error. And this is an error that comes from the fact that we have limited amount of data. So when we teach a simple MNIST task to our models, and this is a task of handwritten digits, this is the smallest benchmark available out there, we use 60,000 images. 10,000 are usually used as your test set, and 50,000 is what you train with. And if MNIST is 28 by 28 images, so it's a handful of dimensions, but it's not too bad, and perhaps 60,000 can represent it relatively well. Then when we talk about CIFAR10, a relatively more complicated data set, but of the same size, but there are at least 3 times as many dimensions, if not more, inside of CIFAR10, then it becomes clear that we probably do not have enough data to actually approximate the task very well. So our data is not necessarily actually capturing all of the variance available in our data, especially in the real world. So you expect your model to either interpolate or extrapolate, or what people practically call generalize over unseen parts of your data, because it's expected that it is capable to deduce them from the data available at hand. The most important thing to take out here is that when we learn, we probably always will have errors. Architectures, learning regimes themselves, or the fact that we just simply don't have enough data to either train the model or even to be able to tell a good model apart from a bad one. It's all empirically estimated. Just to give an example of a super simple setting where statistical error is actually causing most of the problems. On the left, we see 2 Gaussians with relatively fat tails, i.e. we have a lot of improbable events. There is quite a lot of volume here in the improbable events. And let's imagine that we are sampling this distribution. Then if we try to resample the distribution on the left, in this case where there are a lot of tail events, and the distribution in the middle where there is not as much volume in our tail events, we will basically be observing exactly the same image. And as you can imagine, this is relatively problematic, because the image on the left with the distribution 1 and the image in the middle with the distribution 2, they are very different distributions. But if we do not sample them enough, they will look exactly the same, right? And when we ask a question, is 60,000 images of MNIST is enough, we don't quite understand whether we capture the tails of the distributions or not. Right. So what happens when we start training with data that is generated by other models? In essence, what we observe is that probable events, i.e. the events that come from the middles of, in this case, Gaussians, are overestimated, whereas improbable events are underestimated. So the best way to think about this is if your event is in the tail, i.e. it's quite improbable to observe it, then if we sample it a little bit and we will mostly get a picture of most probable things. And then if we were to fit a model over it, we would be treating the improbable events here as the least probable events, whereas the probable events here as most probable events. And this will sway our understanding of what the underlying distribution will look like. And then we will fit it approximately. And this means that our learning procedure, our fitting procedure will introduce its own error. And then we'll get this model to produce more data, which already overestimates the probable events, introduces additional error. And ultimately, this data, if used later on for training subsequent models, is going to really misrepresent what the reality will look like. And as we can imagine, this is going to actually introduce quite a lot of error in our models. Sorry? Should we stop here and take a...
No, I think you're good. I mean, people are adding some are putting some questions in the chat.
Yeah. Okay. Cool. Let me carry on then. Cool. Right. So what do we observe? In the paper, there are quite a lot of Greek symbols. I'm not sure if there is much need to going exactly on what is happening there, but on a very high level, it's really hard to theoretically reason about this stuff because there are way too many moving pieces. So all of the theory we derive inside of the paper is related to single-dimensional Gaussians. They are quite nice abstractions to deal with because they only have a handful of parameters. So it's just a mu and a sigma. And importantly, they don't actually have any error coming from the models or learning procedures. All of the errors that exist in approximating Gaussians is actually statistical error. And that makes it possible to actually reason about them. So there is exact formulas of how to derive stuff. And this allows us to even think about, in practice, what is supposed to be happening with them. It's important to note here that we can theoretically show, and this is just textbooks mathematics, that over time, by representing this as a Markov chain, we absolutely, with a probability 1, converge to absorbing states, and these are delta functions in this particular case, i.e. over time, because of the procedure of losing tails and repeating the process of sampling, fitting, we are supposed to arrive at the point where all of the tails disappear, and we are just left with a single decision inside of it. I'm not sure there is much need to talk about this stuff, but if anybody has any questions, you can put them in chat later on. Here, imagine you are trying to approximate a blue line, a blue Gaussian distribution, shown here by observing just 3 points. If you just try fitting a Gaussian with just 3 points, your Gaussian will look like a purple approximation here. And as you can imagine, this is very far from a true Gaussian looks like. So it is expected that you would sample quite a lot in order to get to this point. When we deal with actually trying to estimate what our error is, on the left we show sorry, okay, let me take a step back. I think I'm flying way too quickly. So here the task is approximating the blue Gaussian distribution. So it's, as I said, parameterized by mu and a sigma. So our mu here is the mean value. We are trying to estimate the mean value of the Gaussian, plus we're trying to estimate the variance of the said Gaussian. In order to do this, we need to sample the Gaussian quite a lot. And the more data points we have, the easier it will become to approximate it. So here we're talking about how many of the axes we have in order to compute the mu estimation plus the sigma, right? So in this plot, we're trying to estimate a normal distribution with a mu 0 and sigma of 1 with a different number of data points. So the blue line here is 100 data points, orange line is 500, and so on. And on the x-axis, we show the evolution number. So this is the generation at which we observe this, i.e., so at the very first step, we have real data, and we sample. So we sample nothing. We just fit the generation 0, evolution 0 on the real data, and then we take this model and we sample 100, 500, 1,000 data points and so on from it, and then we fit the next Gaussian, right, on top of it, and we keep on repeating this. So basically here at 10 to the power of 1, this is an evolution number 10, and in this evolution we have sampled 9 times synthetic data, i.e. this, and we fit basically 9 models, we fit 10 models inside of it. And on the left, we see an error in estimation of the mean value, and on the right, we see an error in estimation of the variance of our distribution. And what we observe here is with the fixed number of points inside, as we keep on learning and fitting this this Gaussian, we observe that unless we have a lot of points available to us, so we're talking about somewhere around 100,000 points, over time we end up swaying quite a lot from the true mean and the true variance. And what that means that even in simple cases where we're trying to estimate a Gaussian with where we know that all of the error is actually coming from the number of points, even in such a case, unless you sample the set Gaussian quite a lot, you are going to be observing the drift. Sometimes this drift happens quite quickly. So in the yellow case, for example, in the line with the in this line, orange, I guess, orange line, we observe that already at the 10th iteration, the error has grown quite a bit. I would guess somewhere by a factor of 1.5 or 2. And then over time, it jumps to a very large number. And if you increase it to 1,000 in the green line, then we observe that the most of the jump is actually happening after like 100 generations. Importantly, when we talk about Gaussians, we usually say that the central limit theorem kicks in quite quickly, and we need like 30 samples. And we clearly see here that in this setting where we are consuming synthetic data over time, that even at 1,000 data points, it's not enough. You will be drifting. You will be drifting a little bit, but over time, this drifting is going to completely screw up any sort of estimation. Right, let me jump over to this. I don't think we have enough time to talk about this. Okay, so I skipped a few slides. We can talk about this a little bit later, but just for the sake of time. In this case, we turn to what actually happens when we try fitting actual real models. So on the slide, we consider something called a Gaussian mixture model. It's again dealing with Gaussians, but it's a mixture of different Gaussians and trying to tell them apart. And on the left, we see the real data. So this is the spread of the original Gaussians. And then when we fit the generation 0 model here, we notice that all of the predictions made by the model are actually correct. They are looking, to my eyes, relatively indistinguishable, and sampling data from it actually gives us a very good solution. And if we were to actually look at the error of the fitted model, it's quite a good model, right? And then we repeat the same process as before. We sample some data points, then we fit the model, and then we use this model to generate more data points. We fit another model, and so on. And we'll notice that by generation 50, your distribution looks nothing like the original distribution at all. And importantly, you'll notice that the variance has decreased quite a bit everywhere. So if before you had points at around 3 and -3, that now we observe that the least probable events are around -2 and 2. And over time, as we keep on repeating the set process, you'll notice that all of the points are kind of losing inside of their variance. And over time, by generation 2000, they kind of converge to a point estimate. It's not really a point estimate. There is still some variance, but it's not that much variance. But the important thing to note here that in this complex scenario, we observe that quite literally over time, the distribution, the original distribution collapses, and it happens extremely quickly. So even by generation 50, it's already quite far away from what it originally looked like. Right. We observed that actually a similar thing happens inside of VEs. Those are variational data encoders. Variational autoencoders, where your latents are also represented as Gaussians. Importantly, we can kind of interpret what latents look like. We can say that if our latents are quite close to the mean, that they are quite probable, and if they are far away from the mean, they are relatively improbable. So on this plot, we show what the distribution of latents looks like for generation 0, generation 1, generation 2, and so on, produce data. So here, generation 0 is data produced by the model trained on real data, right? Then generation 1 is data produced by model 1 that was trained on generation 0, and so on. So generation 2, in this particular case, is data that is generated by a model that was trained on generation 1. And importantly, what we observe here is that if our original latents are distributed relatively normally, so this is what you would expect to see out of a well-trained variational autoencoder, then over time, the data, and I guess I have to note here that here, all of the latents are estimated using the original model that was trained on real data. So we use a model that has a real understanding of what the true distribution looks like to actually then evaluate the probability of generating data from a model generation 1, from a model generation 2, from model generation 3, and so on. So here, we basically, it's as if we ask the original model, the true model, to estimate with what likelihood it would produce a data point from one of its offsprings. And what we observe here is that if the original one has a spread where some of the data that it generates is quite probable, i.e. it's located quite close to the mean, or it's quite improbable, and you will notice that there is very little volume, but it's still volume around -3 and 3, then all of the subsequent data that is generated by subsequent models is appearing more and more probable for our original model. And what that means is kind of the variance in data that is produced by other models which trained on just synthetic data is decreasing over time. It's becoming more and more convinced around the fact that the things that were previously very probable, they basically become a lot more probable. And by generation 9 here, you'll notice that it's basically almost exclusively producing things that are quite probable, and you'll notice that the variance of the produced data has decreased quite a lot. So if before we covered all of this -3 sigma range, so to 99.9% of our original distribution, that here we already are at a state where we only produce things which were originally quite probable. If we talk about what it actually looks like for, in this case, MNIST digits, the original model is quite good at generating digits. They are not ideal, but they look like real digits. By generation 5, they already are extremely blurry, and you'll notice many images share the features amongst multiple digits. So it's quite hard to tell apart. So for example, here, there is a 9, and it's also a 0, and also an 8 at the same time. So, and here, if we look at generation 5, you'll notice those things are already, in terms of probability being produced, they are quite probable. Then by generation 20, they all converged into this mesh of all of the representations fixed together, and all of the original variants, i.e. all of the original data points, they're practically gone. And those models are absolutely unusable, and they do not understand what reality looks like. Although, on average, they kind of look like images. They kind of look like zeros with a little bit of noise inside of them. When we start looking at language models, we observe exactly the same thing happening, although it's slightly more complex to deal with them, purely because training language models is hard. There are a lot of moving pieces. Same setting as before. We observe different generations of models. Here we take a pre-trained OPT model. So we're not training the original generation 0 model. We assume it's pre-trained by Facebook. And then we use it to fine-tune Wikitext2. It's another data set. And we observe then the perplexity of generated data points. So this is basically the probability of generating a sequence of tokens. And important here is the closer to 0, the better is the probability number. And here we plot a density as well. So we observed that for generation 0, so the very first time we fine-tuned on top of Wikitext, we get quite a lot of variance available to us in our language models in the sort of data it generates. Yet over time, just like we observed with our VEs, and just as we observed with the GMMs, our variance disappears. So our basically the observed distributions, they kind of get closer together. And also because here we measure the error slightly differently, it's the probability of generating this sequence, our perplexities are kind of shifting towards the left. So, and this is all estimation of the original model, similarly to the way we're treating VEs. And the way to read this is the original model is thinking that the data that is produced by subsequent generations is extremely probable. So it basically thinks that whatever data my subsequent generators are producing, in majority of cases, it's what I would produce with a very high probability. But at the same time, sometimes we observe that the tail events, i.e., those are going to be the errors of the learned solutions. So it's basically an error that is coming from either fitting the model or the architecture itself, is basically giving us data that our language models should not be producing. Interestingly, we also observed that exactly the same sort of phenomena is happening when we actually use some of the real data in training alongside synthetic data. And it's also shifting to the left, but not as much. So clearly using some part of real data alongside the synthetic data is helping to contain some of the effects of model collapse, but model collapse happens nevertheless. So your models start producing things which the original model was quite probable to produce, and it's also introducing its own original error, but the effect is not as pronounced. When we talk about what it actually means in terms of language, so here we give an example with a quote from Wikitext where it's talking about the architecture of some church in England, and on the top we see the original input, and then this is what generation 0, generation 1, 5, and 9 are producing to continue the text. And we can see that generation 0 and generation 1, they talk about something which is relatively related to the original input. So the degradation is not as pronounced. Then by generation 5, we'll notice that it starts talking about something not very much related to the original input text, to the original text input, but it's still making some sort of syntactic sense. And it's just talking about languages, just listing the languages. Not sure why it's not really very much related to the original input. And then by generation 9, it just finishes the sentence above, puts a dot, and then it starts talking about birds, just as if it was, for whatever reason, but it's just listing birds and going in the circles. And as you can clearly imagine, this is not very much related to the original input. So it basically starts being convinced that I should be talking about some sort of very highly probable event, just, populations of birds. And it keeps on doing this. And the longer you train those models, the more you observe, the more you notice that over time, language models basically start trembling about something unrelated. That's basically what's happening. Right. So it is worth mentioning that although model collapse is general, i.e. we can show it that exists theoretically and it should with probability 1 always happen in a setting. In the paper, and also empirically, we also observed that exactly model collapse is happening, and we can kind of even predict sometimes what the model collapse should look like. The study comes with a little bit of limitations. So first of all, we assume unbiased sampling for almost all of the cases except LLMs, because LLMs usually generate data in relatively odd ways. And what that means is it may not necessarily represent the most of realistic settings, because we sample our data in a relatively biased way. We don't want data which represents all of the distribution. We very often only care about probable things. So, and that means that in reality, maybe with some additional filtering or maybe in some sort of active learning settings, model collapse is going to behave relatively differently. Next, we only, the largest model we tested for is OPT 125M, which, although a large model, is not a very large model. So we may discover that if we start dealing with even bigger models, even more parameterized, over-parameterized models, maybe it's not going to be drifting as quickly. So the model collapse maybe is going to be slightly slower, I guess. We definitely need to do more experiments with fuse data. So in the paper, we only consider the cases where all of the data comes from the previous generation of the model. But I'm certain, and we assume that it's only a single model that the data is coming from. I'm certain that it's going to behave relatively differently when we have multiple different models giving data to the subsequent generations. And at the same time, if the data actually comes from different generations themselves, so not only generation n-1, but also n-2 and -3 with a certain probability, we need to study more of the impact on fairness. We hypothesize in the paper that because we first observed that our tails are shrinking, so the minority classes and minorities represented in the original data distributions are going to be suffering the first in model collapse, but we don't have the real evidence to show this. This is more of a hypothesis, and it would be great to study fairness impact. And importantly, we probably want a much more expressive and manageable way to model the model collapse phenomena. Our current theory is relatively general, and I'm sure there are ways to model this in a much nicer way where we can actually predict behaviors and say that for a generation X, we need to sample n times more data in order to contain effects of model collapse. And this is something that is not really possible as of yet in our current theoretical work, except for the Gaussian, single-dimensional Gaussians. For them, we can do that, but it's not very useful. Right. Just to summarize, model collapse is real, both theoretically and empirically. We observe that training with synthetic data causes degradation of our models relative to original data distribution, and it will happen. So we have to take explicit care into dealing with our data and making sure that there is a lot more signal in the side of our data and a lot less noise. And I guess this
is great. Yeah, this is great stuff, Ilia. I think it's a pretty profound conclusion that, I was struck reading the paper, and what you just said there is that not only is it inevitable, it's an artifact of the statistical error itself, but it's also irreversible, right? And as both in models being deployed at individual businesses, but also kind of these big models, the effect is unavoidable, right? We've got some questions in the chat. Could you go back a few slides? There was a couple of points about there was the one with the digit generations with the blurry images.
Yeah.
And one of the questions here is exactly what is causing the blurring? Like, why is it blurry from generation to generation?
there are many reasons here. My hypothesis would be this is an artifact mostly of the architecture error, because my assumption is it's just the fact that it's a convolutions based VAE here. So, and for convolutions, they're not very good at actually telling apart things. It's
Right.
yeah,
So-
basically, I would assume that I don't have an answer to that question. Why exactly they become blurry?
Mm.
But my hypothesis would be that this is an artifact of the architectural error. Remember how I said that there are three sources of error usually with this? It's either the model architectures, the learning procedures themselves, or the fact that we don't have enough data. There, we clearly have enough data because we sample exactly the same amount of data points as they originally were in the original distribution, i.e. 60,000. And it's either going to be learning procedure error or the model architecture itself. And my hypothesis would be that it would be model architecture, just from practical experience playing with VEs and trying to get VEs to do things that they're not supposed to be doing. So I would just guess that if we were to pick some sort of other obscure architecture with, like kernel size 1 or something, maybe it will not be becoming blurrier, but rather it will look slightly differently. But nevertheless, like the sort of probabilistically, it should behave in exactly the same way, i.e. it should start converging into some sort of data representations which are very, very probable. So maybe instead of becoming blurrier as they did here, they will stay sharp as they were before, but they would be like overlay of multiple different images, but still sharp in some way.
I think it's on this slide too. There's a question here from Shiv. Is Gen 20, well, I guess D there, considered to be a model that has overfitted the data? Could we call this an example of overfitting, or is it a different phenomenon? Or Shiv, if you want to add something to that, you can unmute and ask.
I guess maybe in some way I would, I'm not sure that's a good description, purely because you are overfitting to a part of your distribution, let's say, not really the whole of distribution. It's I would not call this overfitting necessarily. This is more like overestimation of probable events. Sorry, can you repeat this?
Shiv?
Could it be considered overtraining? Is that is that even a term? Probably not. I don't think, but
yeah, I'm not sure. I mean, in some way, it's kind of overtraining, because what is probably happening here is, maybe overtraining is a good way to kind of, on a very high level describe it, where you are basically focusing way too much on things which are probable and start forgetting things which are not probable. But as you are focusing on very probable things, you keep on introducing new additional error inside. So it's kind of...
So in these situations, all the non-probable events need to be trained. You need to have a substantial amount of data set, even though they don't occur as frequently. You still need to have a large data set of that. Otherwise, you end up with situations like this, right?
Yeah, but it's important to note here that it's not just about it's not just about the frequencies at which they appear there, because in principle we should capture them quite well by unbiased sampling. But it's more about the actual representation inside as well. So we already know from our current fairness literature that when we learn on, like, in the settings where we have a majority minority class, most of our error is actually accumulated in our minority classes. And that means, like, when you generate data which is representing the majority, your error is going to be quite low. But when you're generating data from the minority, the error is going to be quite high. So if you proportionally sample the same amount of data as before, you'll discover that in terms of the amount of signal in your minority class, it's going to have a lot less signal than the majority class itself, right? So it's not even just about the raw numbers and proportions. Like, it's not enough to say, oh, we have minority class represented as 10% of the overall data set, but it's also on top of it just making sure that internally there is as much information about the original task as there were in the original distribution.
This leads to a question that Colin asked earlier. Does it help? Like, what if you just oversampled tails, like oversample that minority data?
Yeah, so it should in principle help with just degradation and the tail events. I would imagine that we will still be degrading in overall performance as well,
Right.
still, purely because even if you just wanted to account for the tail error, you will still be introducing error. So from statistical error inside of your tails, you will still be introducing additional error from learning procedure artifacts plus the architectural artifact. So the error will be adding nonetheless. You
Right.
can get some sort of limitations on top of statistical error, but model collapse will still be happening.
You had mentioned before, Ilya, that in the GPT-4 paper, for instance, they talk about using synthetic data to retrain their own model, and that that they were using that to reduce the likelihood of hallucinations, right? Does that affect, or did they get that reduction in hallucination because of this effect you're talking about, because of the statistical artifacts, or did they still do it anyway despite the drive to model collapse, like just because it was cheaper?
I think it's a question for them. I would hypothesize that it's given how hard it is to train those models, that it's purely what worked for them, for their benchmarks. In principle, most of this field is alchemy, pure alchemy, as in you never know why stuff works. So I would just suspect it's just what they found, that it works quite well. If you look at their papers, though, sometimes, like in the same Instruct GPT that you mentioned earlier, if you look at the sort of regularizations and optimization procedures people use, you kind of get a feeling that this sort of effect is what they model for implicitly, but I'm not sure if when they were training their models they quite literally thought about this, and this was the primary reason rather than accuracy. But yeah,
right.
I hope this answers the question.
We're at 1 right now, so if people have to drop off, that's fine. Ilya, if you have to go, let me know. There's still a few questions here. Should we?
I'm happy to talk more. I have time.
Okay, good. There's a great question here, Shael. Do you want to unmute and ask about that? So we're back to the pure Gaussian model you used. Can you unmute? Or you? Yeah, great.
Yes. Yeah. Can you hear me?
Yes, I can.
Great.
Yeah. So you pointed out that in the case of pure Gaussians, if you model the process of learning from synthetic data, you are getting that the Markov chain is converging into a delta function, right?
Yeah, it's converging to some sort of an absorbing state.
Yeah. That is a bit surprising, but could you compensate for that in the process? Like, if you
yes,
know...
yeah, exactly. As a matter of fact, we derive how much you need to compensate for, and basically you'll find that you need to superlinearly sample over time. So basically, with every new generation, you need to get at least linear increase in the amount of data you sample for, just to account for statistical noise.
Okay.
It's all covered in detail in the paper. Yeah. So, and if there are any more questions around this, just ping me, and we'll figure it out. But yeah, in case of Gaussians, you can actually model it quite nicely. In case of everything else, we couldn't come up with a way to do it.
It's remarkable that this is an effect, again, born of the mathematics itself, right? It's not based on necessarily on the quality of the data. It's just how if the data is fed back into the same system. Min, I'm not sure if that's your actual name, MINH, got a good question about introducing more complexity to the model itself such that it can retrain itself. Wait, where are you? You want to unmute?
Yeah, hey, I was just wondering, like, if model collapse is inevitable, right, then should one just not use synthetic data at all, right? And or is it that we should use synthetic data because we want to get certain outcomes quicker, and then somehow train it later to, quote unquote, fix the model, whether it be with non-synthetic data or introducing some other model that can correct the model. I don't know. So,
Yeah, so, okay. It's important to note here that it's not really possible to separate synthetic, non-synthetic data, especially if our synthetic data is, statistically indistinguishable from synthetic data, so like non-synthetic from synthetic data. And this is practically what all of this learning of the distribution is. We are trying to produce things which are as representative as the original data. So in principle, the problem here is not the fact that we are deciding whether to use synthetic data or not to use it. Unfortunately, we absolutely have to use it. And because it's already overpopulating us. Like, imagine for a second right now scraping Twitter for the past, most popular 1,000 tweets. Like, there is a very good chance that big majority, or maybe not a big majority, like quite a significant proportion of them are going to be automatically generated in one way or another. And it may be like, proportion of it is human, and then proportion of it is paraphrased by ChatGPT or something. Right.
Last week we had Long you on here and to talk about reinforcement learning, human feedback, and we started to talk about reinforcement learning with AI feedback, right? As some of the models are doing now. Is that prone to exactly the same type of model collapse you're talking about, or because the training model is different from the generative model, that effect is lessened?
I'm not sure I understand the question. So are you asking why training with your own data in case of reinforcement learning works, but it doesn't work here?
No, I was asking more specifically, like with the reinforcement learning with AI feedback, with those models, are they prey to this exact same kind of model collapse that you're talking about?
Are you assuming RLHF, or is this
RLAIF, right?
Oh, RLAIF.
Yeah.
Interesting. Okay, let me think for a second. So for those who are not familiar, people use RLHF. This is a technique that basically tries to align preferences in the generation phase, or some sort of sampling phase, with the preferences of a human. So there are a lot of human raters that basically, given a pair of samples, express preferences over one sample versus the other sample, and then you can kind of like sway distribution of outcomes towards human-like. So what you're asking is, if we replace humans with automatic systems, how well will this work? Can this stop degradation? Well, it's a little bit. Okay, so my response would be, I would imagine that model collapse should still be happening, maybe perhaps even faster, purely because, so you're still going to be overestimating probable events, and probably overestimating them even worse, especially if it depends what the distribution of preferences will look like. And similarly as before, your learning should have artifacts. And even if you assume that all of the learning artifacts will kind of disappear because we are going to be expressing preferences over things which do not have errors, you are still going to be accumulating statistical error over time, especially the more you bias your sampler. Yeah. So the answer, it should be degrading in the same ways.
Right.
But on more specifics, I'm not sure. Yeah.
It's a kind of a similar kind of question. Does the model collapse happen faster or kind of more catastrophically if the model is only being trained on its own data, or like, if we use a variety of models, a diversity of models, do the statistical effects kind of cancel each other out, or does it forestall?
So that's a very good question. And as I mentioned in the limitations, that's basically one of the most interesting questions, because in practice, when we talk about learning with something like differential privacy, where we, on top of our data points, add like zero mean noise, we make an assumption that on average this noise is actually not going to do anything for us. So any sort of like more formal definitions of privacy relying on noise which is not correlated with itself, right? So we can quite easily decorrelate it on a distributional level. This should in principle work quite well. The problem comes from noise that is correlated, right? So if you imagine that you had like a wide variety of models, but they were all trained with SGD, then you are going to be absorbing SGD noise over time that is added inside, right? And in this regard, basically, yeah, we're still going to be observing model collapse, but perhaps it will take a slightly different shape inside. But maybe this is enough to actually sustain most of the error. It's not too clear to us. We haven't yet had time to look into this.
This is fascinating. We could go on forever. I want to be respectful of your time, though. And oh, wait, we got one more question just snuck in there before I wrapped it up. Carrie, do you want to ask directly?
Yeah, so I was wondering if you could largely ameliorate the model collapse if the sample had a certain proportion of real data. I think you had a slide that showed that 10% helped, but I'm wondering if you go up to higher proportions. Sorry if you covered this and I missed it.
No, not at all. I did not cover this. So in this particular paper, we have not looked at more higher original data proportions. I think nowadays, after we released the paper, there's been a couple of other studies looking at the similar phenomena, what they did, and they find that over time you need to keep on adding real data. But in this particular paper, we have not now. Unfortunately, at the time when I was writing this, I had limited computational resources, and that in turn meant that training even something as relatively small as 1 to 5 MOPT was a little bit of a pain, especially given that you can't really parallelize it because it's a sequential process. You have to kind of wait for things to finish. But yeah, it's a very good question. Unfortunately, I don't have an answer to this. And I would suspect that it's a question of what type of task you're modeling, because if you're thinking about like language, there is quite a lot of variance in language. So if we're talking about just statistical error itself, then it's a question of capturing all of your variance, plus at the same time making sure that there is no additional error from learning, or if any sort of error from learning is added inside, you're capable of decorrelating signal from error and only focusing on the signal itself. So yeah, I suspect that this is case-by-case basis, and there is no real way to analytically answer this.
I mean, there's so many interesting implications here, including which you briefly mentioned in the paper, the idea then that as we move forward, that human generated data is going to be worth a heck of a lot more, right? I imagine a kind of like a Mad Max scenario where everybody is fighting over this scarce resource of the real data.
I mean, that's basically what is happening right now already, right?
It's true. Yeah, it's true. Great. Well, this has just been fascinating. I think this is a really profound conclusion. I feel like this is going to be like, you know how people talk about that moment at that conference in Vienna in 1930 when Gödel kind of was like, this is the incompleteness theorem, you guys. And everybody was like, well, okay, we're done. Like, there's nothing we can do about this. It's just
I am humbled by your words. That's
we'll see. This is change everything, right? Great. I just want to thank everybody for spending some time with us. And this is a great discussion. We can keep it going on the Discord server, which I think you are all on probably now. And in 2 weeks, we're talking with Lian-Hui Quinn on reasoning in large language models, abductive reasoning, common sense reasoning. This is work that Vered Schwartz from the University of British Columbia had presented a little while ago at the Vector Institute, and she introduced me to Lian-Hui. So yeah, I'm going to stop recording. I will post the recording in case you want to use it for reference. And thanks, everybody. Elena, any last words from you?
Just huge thank you to Ilia. Really, really insightful session. And thanks everyone for coming in and joining us. I added a link to a feedback form for the session. If you want to fill it in, it would be great. So we can make it better and keep growing the group. But yeah, thank you. This is really fun. It's made me think of a movie Inception of the mirror scene. And Ted Chiang's article on the blurry JPEG of the web, those are really interesting questions, where this is all going and how it's impacting the web as well, as we are giving more human feedback to the model directly versus participating in communities like Stack Overflow, which are already losing to ChatGPT and the like on the interaction front. So yeah, thanks so much for this.
Thank you very much for inviting me and having me.
Great.
And the comparison.
Nice. Okay. Well, thanks again, everybody. Have a good rest of your day. We'll see you soon.